In this video, we're going to derive the Pushforward or Jacobian-vector product rule for linear system solving, or the solution to linear systems of equations. You can maybe think of them as a function that takes a matrix A as well as a right-hand side vector B and is then given implicitly by the solution to a linear system of equations. So we could say solve matrix A times vector x equals right-hand side vector B for the vector x, and let's denote that result as x. So you give it a matrix, you give it a right-hand side, it solves the system. Such problems are fundamental to numerical linear algebra. So you'll find them, for instance, in the numerical solution to PDEs. So for instance, if you want to do implicit time stepping, you have to solve linear systems, or if you compute the solution to the incompressible Navier-Stokes equation, you have to solve Poisson problems in order to solve for incompressibility. This is a linear system. You will also find them as part of optimization methods or also root finding methods. So for instance, if you want to apply Newton-Raphson schemes for nonlinear solvers, then linear solvers are a substep of it. So you do a couple of linear solves in order to do a nonlinear solve. And they have so many more applications. They are the fundamental building block of everything implicitly done in numerical linear algebra. There are also a ton of algorithms in order to solve these problems. Usually you distinguish between two types. First, there are direct methods. Direct methods usually rely on the factorization of the matrix. So classical examples would be LU decomposition for general matrices, but also Cholesky decomposition for symmetric positive definite matrices. These are usually the methods you use for small systems. So let's say systems with 1000 by 1000. There are also sparse counterparts that can handle larger sparse matrices and do sparse factorizations. But generally, if you encounter very large systems, as they are part in like solutions to three-dimensional PDE problems, you most likely rely on iterative methods which approximate the solution to this linear system of equations. And there are also a ton of algorithms. Most notably, there is the conjugate gradient method, which works for symmetric positive definite matrices. So for instance, those arising in the pressure correction problem for incompressible Navier-Stokes. There is also the really famous multi-grid method, which has an extremely nice theoretical complexity. But there are also other approaches for specific type of matrices. Let's also talk a little bit about the dimensionalities here. So let's say that the matrix A is an n by n dimensional matrix. The vector B shall be an n-dimensional vector, and as such, the solution to the linear system, here denoted by x, will also be an n-dimensional vector. And here we will just assume that this linear system is solvable. This, for instance, means that our matrix is not singular, and it's also a well-behaved system, because what we want to do is to forward propagate tangent information from the input to the output. This could, for instance, happen if your linear system is part of a longer computational chain. So for instance, think of a differentiable physics simulation in which you do the pressure correction for the Navier-Stokes equation. But you not only do it once, you do it a couple of times, and this builds your computational chain. And now you want to do automatic differentiation on it. And here in this particular example, it's for forward mode automatic differentiation. There will also be a video for the backward mode, the pullback, but here we want to forward propagate tangent information. So let us note this down. The task for this video, or why we do the derivation, is to forward propagate tangent information on the input, and this will be in terms of a tangent matrix. So it will be a matrix, and we indicate that with a dot on top, and this one will be of the same shape as the Primal matrix, so it's an n by n dimensional matrix, as well as tangent information on the right hand side, which will be an n dimensional vector. And then we want to propagate this to the output, and this output will be x dot, which is another n-dimensional vector. And as said, this will be part of a longer computational chain for which we then apply this forward mode automatic differentiation. And so we have to be able to propagate this tangent information. As with all these kind of implicit approaches, let it be linear systems, let it be nonlinear systems, but also generally the solution to ODEs and PDEs, there's typically two ways to do that. The naive way, I would say, is to just do forward mode automatic differentiation through the solver. So, but this is what we do not want to do. So let's say without forward mode AD or automatic differentiation through the solver, and the through is critical, so through the solver. What do I mean by that? As with any kind of numerical algorithm, it is composed of smaller computational steps, some multiplications, matrix vector products, etc. If we unroll or open the black box to an algorithm, we could just apply the smaller forward rules on these particular steps in the computational chain. Sometimes this is possible, and it's also sometimes a valid alternative to what we're going to derive here, but oftentimes this comes with some troubles, some numerical instabilities, or also maybe the inability to do so, because oftentimes these low-level numerical algorithms, like the solution to linear systems of equations, are implemented in a highly efficient manner, which often does not allow naive forward mode autodiff through it. And so we need to be able to find an alternative. And this is what we're going to do in the video here by the help of the implicit function theorem. Just to note that down, this differentiation through the solver is also called unrolling or also piggybacking. And I think that's quite an interesting metaphor, because we are piggybacking or putting the tangent information on top of the primal information and just pushing it also through the solver, if it is possible at all. Okay, so we want to find an alternative. For this, let us note down the general push forward rule. So in general, what we're going to do is we will find the tangent on the output by taking the Jacobian of our function, so kind of linearizing it, and this will be df by the first input a, and then contracting it with the tangent information. And here I'm using the colon operator because the derivative of the function, which has a vector valued output with respect to a matrix, will give us something like a rank 3 tensor. And in order to contract over 2 ranks, we need the colon here. It's a little bit loosely here in symbolic notation. It will make sense in a second when we go to index notation. And then we add up the second input to the function, so again linearizing f, but with respect to b this time, and then contracting with the tangent information on b. Okay, let us write that down in index notation to remove the ambiguity of how these operations are done. So let's move to index notation. But before we write down the push forward rule in index notation, let us first write down the primal or forward computation. So the one we would be doing anyways, which is the solution to the linear system of equations. And this is in that we have this implicit constraint that aij, so I was just arbitrarily selecting the indices here, multiplied with xj is equal to bi. And this has to be solved for xj. Then the push forward will therefore be, okay, let's take our x dot and let's also give it the index j here and say this is equivalent to saying that the derivative of f index j with respect to akl is multiplied with a dot kl. The function f has a vector valued output, so we will index it at the same point as the particular push forward tangent that we want to have, and then derive it with respect to its first input. Let's introduce some new indices, here in that case k and l, and then by the Einstein summation convention we contract over 2 times appearing indices, and here we see this is the double contraction, so we contract over both k and l. Then let's add dfj with respect to bk multiplied with tangent bk, and this is what we now have to implement. I just want to give these 2 summons a name, so let me introduce some arbitrary naming here. Let's call this one the tangent xj and then upper index a, the contribution from the matrix, and then this one will be the contribution from the right hand side. And in order to evaluate that fully or to come up with a closed form solution is that we have to somehow find an expression for this Jacobian. The function is given implicitly and we have to find a Jacobian for this. Well, it's going to be a little bit tricky. Let's do the 2 Jacobians here separately. Let's first do this one here and say 1 and then do that one here. Okay, let's go with 1 first. The Jacobian of the linear system solver with respect to the right hand side. So dfj with respect to dbk. And here we're going to use implicit differentiation. So this is a consequence from the implicit function theorem. And by this we take our primal or our condition that has to be fulfilled as kind of implicitly and derive it with respect to bk. So what we get is the derivative with respect to bk of aij xj, and then on the right hand side the derivative with respect to bk on bi. Okay, let's do the right hand side first. deriving bi with respect to bk, so we are deriving a quantity with respect to itself. In a one-dimensional case, if you derive some y with respect to y, this will be 1. However, in the high-dimensional case, if you derive two identical quantities but at different index positions, you will get a 0, and we will encode that with the Kronecker delta ik. So to say, the result of this differentiation is 1 if the indices match and 0 otherwise. Let's go back to the left-hand side. And if we then look at our product of aij and xj, we see that the aij does not depend on bk. So the system matrix does not depend on the right-hand side. Whereas obviously the solution to the linear system depends on the right-hand side, because if we change the right-hand side, our numerical solver, the function f, would give us most likely a different result. So in that case, we will get aij multiplied with dxj with respect to bk. And the quantity that we found here is exactly what we're looking for. So this, the Jacobian of xj with respect to bk, is equivalent to the Jacobian of the function with respect to bk, because we can associate the function with its output. So this is exactly what we have here. So let me also highlight that. This is equivalent to fj with respect to bk. So this is what we found here. But in essence, for the push-forward rule, we are not interested in just the Jacobian, but the Jacobian being right multiplied with the tangent vector. Therefore, we also call it the Jacobian-vector product. And we can find that here, or the contribution to it, the xj.b contribution, in that we right multiply this equation with b.k. And then we get aij, then this quantity either written with the f or with the x. Let's keep the x here and say derivative of xj with respect to bk multiplied with dot bk is equal to delta ik times dot bk. Then let's identify this one here is essentially the contribution we wanted. So this one is our xj dot contribution from b. So xj dot contribution from b. And on the right hand side, we can apply an index change. That's what our Kronecker delta induces. So we can change the index from k to I. So we will have aij with bk, no, not bk, but bi. And as such, we see that we will get the contribution from the b side as another solution to a linear system of equations, because we see this has the same format as our primal. So it's implicitly given. Let me just note that down. This is another linear system of equations. Don't worry, we will formalize that again later on and come back to this point. Second, let's now do the other derivative. So the derivative of the function with respect to the matrix. So this one is the one that is a little bit mind-bending, because we are deriving a vector with respect to a matrix, some kind of a rank-free tensor. But the idea is the same. We do an implicit derivative. And in index notation, we removed a lot of ambiguity of that. So let's take the derivative of something with respect to akl, and that something is aij times xj. So this was the primal. And the right-hand side derivative with akl of bi. Let's do the right-hand side first. So if we derive a quantity, right-hand side b, with respect to the matrix, they don't depend on each other, so this will just be plain 0. But here we now have to be careful, because we have the product rule. So both a depends on a, obviously, but x also depends on a, because if you change the system matrix, the solution to the linear system would obviously be different. So let's first do the derivative of a with a. This is the same as with b, but now with two indices. So if we take the matrix index ij and derive it with respect to a matrix index kl, it will be 1 only if both indices match identically. So we can express that by the help of a multiplied Kronecker delta. So delta ik multiplied with delta jl times xj, because of the product rule, plus, and then now the derivative of xj with respect to akl. So we will have aij, this stays as is, and then we have the xj with respect to akl. And similar idea as above, this is essentially the quantity we're looking for, because we associate the function's output with the function. So this is the same Jacobian as we have it here. So this one is essentially dfj with respect to akl. And then let's do the same trick as before. let's multiply with the tangent, but in this case it's tangent AKL. So let's multiply from the right with AKL tangent, and then we get that delta IK, delta JL, xj times tangent AKL plus AIJ times dxj with respect to dAKL times tangent AKL is equal to 0. And here we see that is again the quantity we're looking for. This is tangent xj with the contribution from A. And then let's do the indice change as we've done it also with the B contribution. So what we will do is we move the index from L to J and from K to I. So here we will get xj multiplied with tangent ij plus aij, and then that one here. Let's rearrange, and then we will get that aij times xj tangent contribution from A is equal to minus, and let me also swap the order here to make that a bit more clear, tangent aij times xj. So here we have another solution of a linear system of equations, because the contribution is again given here implicitly, and the right hand side is a quantity we both know. So we both know the tangent on A, that's an input to our push-forward rule, as well as the primal solution, because as with any kind of automatic differentiation, a primal pass, so the original solution to the original problem, will always be part of the computation. So this xj is also known, so this is just a matrix vector product, and as such we could maybe also represent this as some artificial right-hand side vector, and we need another solution of a linear system of equation. So let's say this is another linear system of equations. Now it's a time we can go back to symbolic notation, because we've now gotten rid of all the rank-free tensors for which an index notation is favorable. So let's say we go back to symbolic notation, and then we see, well, first the contribution from 1 is that we will get the x tangent contribution B is that we solve another linear system of equations with the same matrix, but the right hand side being the tangent information on the right hand side. And then we will get the contribution from A by also solving another linear system of equations, and this time the right hand side is minus tangent information on A multiplied with the primal solution x. And now we see that in order to propagate this information, we have to solve something similar to the primal problem twice in order to get both contributions and then add them up. However, we can also see that due to the linearity, we can fuse that into one linear system solve. So let us do that. We fuse the two linear system solves into one. And of course, this obviously reduces the computational load. And by this, we know that the x tangent dot is given as the contribution of the x tangent from B plus the contribution of the x tangent from A. And let us now loosely speak in terms of matrix inverses. So this will be the inverse of A multiplied with B dot. So this is from this contribution here, plus the inverse of A multiplied with minus A dot x. And just to remind you here, you cannot multiply the inverse with the tangent. This will not give you the identity. So of course, if you multiply an inverse with the original counterpart, you will get the identity. But here, this is not the original counterpart. So it is another matrix of the same shape, but it has different numerical values in it. So it has the tangent values in them. But what we can do is we can fuse the two together. So what we get is that this is the solution or the matrix inverse multiplied with the tangent on B minus A dot times X. In order to now make this a little bit more clear, let's go back into the form of a linear system. So what we see that hence as total, we find that A times X dot, or the tangent that we want to have, is given as B dot minus A dot times primal X. Or even more expressed is that we will find X dot as the solution to another linear system. So let's solve A times X dot is equal to, and let's call this maybe the vector D for X dot, and with the vector D being given as B dot minus A times X. And with this, we can now formulate the full push-forward rule. So this is what we're going to do next, the full push-forward rule. So we will push forward tangent information on the function f, which was the linear system solver, given the primal inputs a and b, as well as tangent inputs a dot and b dot. And crucial, these are all given. So you have the numeric values of a, of b, and a dot and b dot, of course. So first you do a primal solve, and I want to make this a little bit loosely here and speak in terms of inverses. Of course, you know you should never do the inverse, but you should use some direct method or iterative method to solve the linear system. So what we will get is that this is matrix A inverse times B. Obviously, that's the primal solution, that's our x. And then we push forward the tangent information by solving A inverse times B tangent minus A tangent times primal x. So this is essentially then our x dot, how we propagate that. And in order to solve that, we need to incorporate this primal information. So that's why these two are kind of intertwined. And that is our full rule. Let me put a box around that. Yeah, a pretty ugly box, to be fair. And a last remark I want to make about that is that we can even reduce the computational load for the tangent pass by quite a bit if we reuse factorization in the case of a linear method. So what we see here is we need the inverse of a matrix twice. Essentially, if you were to use a direct solver, like an LU decomposition, a Cholesky decomposition, you would factorize the matrix and then can use the factorization to solve the linear system. And usually the factorization itself is something that scales cubic in the number of dimensions, so it's O of n to the 3, whereas the there following solution of the backward or forward substitution is something that scales quadratically. And if you already have the substitution from the primal pass, you can also push forward tangent information at something that scales quadratically. And that's quite a nice insight here. In the case you use direct methods, let's say reuse the factorization in case of a direct solver. But what you can also do in case you don't have a direct solver and you rather have an iterative solver, and as part of that iterative solver you use a preconditioner, you can also reuse the preconditioner. So we can also reuse the preconditioner if there is any, and probably if you're solving really large sparse linear systems like those with PDEs, you most likely have a preconditioner. So reuse the preconditioner in case of an iterative solver. And that's basically it. That's how you would forward propagate tangent information over the solution to a linear system of equations. So you have this solution as part of a longer computational chain, your differentiable physics simulator, and you now want to apply forward mode automatic differentiation. That's crucial. The rule for reverse mode looks a little bit different, and we will derive it in the next video. The big gist is that you will have to solve another linear system of equations. You will solve a similarly complex problem in the tangent pass as you will do in the primal pass, but often you can share some workload between them, especially if you did some factorization or a preconditioner. A big thanks to all the patrons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you will find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There is more awesome content on automatic differentiation rules or automatic differentiation in general, or maybe you're interested in how to embed these ideas in order to create a differentiable physics simulator, then also stay tuned for future videos. Here you will now see similar videos, and I hope to see you in one of the next videos.